Okay, so the next thing I'm going to talk about is Faraday's and Lenz's laws. Faraday's law of induction basically went into talking about, okay, what things will affect the induced EMF. Now, before we actually get into Faraday's law itself, we got to define something, something called magnetic flux. Okay, now if you look here, there's these couple symbols here. Now this one is the one that you're going to find in your book, your Giancoli book. This is the symbol that you're going to see on your AP packet. Okay, but they're the same thing. So just so you know, the symbol for it looks like that. Okay, this one I think is fairly self-explanatory. It's got the B for magnetic. This particular symbol, the name of it doesn't necessarily matter that much. This one here again's got the little M for magnetic, but it's the magnetic flux. Both of these have little lines that pass through like a little circle. That's going to be important here for us, okay? Because what exactly is magnetic flux? It's really hard to kind of define magnetic flux. I've heard in the past that it was called the line density. That's not necessarily exactly accurate, but I've drawn a picture here of the pole of a magnet, okay? If I say had a piece of paper, okay, and the piece of paper was only as wide as this magnet, okay? If I put the piece of paper here, then all 5 of those lines would travel through the piece of paper, okay? If I move the paper up, only 3 lines pass through the piece of paper. And if I move it up even further, okay, well then only 1 line passes through the piece of paper. Okay, so essentially what magnetic flux is how many of those lines, okay, or how much of the magnetic field is actually passing through the area where we're trying to induce our EMF. Okay, so I've got another picture over here that just has a flat sheet, okay, and then lines traveling through it. The amount of lines is proportional to what's called the magnetic flux. Okay, now we measure magnetic flux by saying, okay, what field lines are perpendicular to the area, okay, but if those lines aren't perpendicular to them, okay, if they're at an angle like this, then we always measure the angle from perpendicular. Now this can be a bit confusing. If you look at the equation here, we've got the magnetic flux is equal to the magnetic field times the area, and then there's the cosine of theta. Now, this is where it can be a bit tricky. They always measure the angle from perpendicular. So when this angle is 0, that represents perpendicular. That is the maximum amount. You get a value of cosine of 1, okay? Or cosine of 0 is 1. If you do the cosine of 90, they would actually be parallel, and that's because it's 90 degrees from perpendicular. That's what it means. Okay, so this can be a little bit confusing. It's not necessarily super intuitive for you. Okay, but this is the basic definition of magnetic flux. What is the field passing through the area, and how much of that field is perpendicular? If it's not perpendicular, you take the component that is perpendicular to it. Okay, so I've got a couple more pictures here. Okay, so if I have a field drawn like this, and I put a loop of wire into that field. If I put it like this so that it's parallel to it, none of those field lines pass through the wire. Therefore, the angle is 90 degrees, and the flux would be 0. If I start to turn that coil of wire, okay, let's say to a 45-degree angle, well, then we're going to get some flux. That flux will be greater than 0. And if I turn it completely perpendicular, then the angle will be 0, and we actually get the maximum amount of flux out of it. So again, you can think of the flux as being proportional to the total number of lines that pass through the area of the loop. There is a unit for magnetic flux, and it is called a Weber. 1 Weber is a Tesla meter squared. Okay, and that should make sense from the equation. This is in Teslas, this is in meters squared. Okay, so getting us actually down finally to our law, Faraday's law of induction. He found that the change in the flux, the rate of change, delta flux, was proportional to the EMF, and then also the amount of time. So the slower you introduce the magnetic field, the smaller the induced EMF, the faster, the quicker the time, the shorter the time, the faster you moved it, the higher this value went up. Now, I've drawn this as if it was just one loop of wire. If you use multiple loops of wire, okay, you have to include the factor that takes into account that you're using more than just one loop. So if you were using 10, you got to multiply the whole darn thing by 10. Okay. You'll also notice that there's a negative sign in there. The negative sign tells us the direction that the EMF acts. Okay. So that leads us over here to Lenz's law. Lenz's law says a current produced by an induced EMF moves in a direction so that its magnetic field opposes the original change in flux. Now this is going to be something where when you say it out loud, it's not going to make any sense whatsoever. So I want to go back and I want to take you to a picture from the last video that I did. Okay, so let's just talk about this. If I take this magnet, okay, and I introduce it into this coil, so I'm taking the field. My fingers are the field, right? If I'm taking the field and I'm putting it into this coil of wire, the wire itself is going to produce a field that opposes it, that goes down, that comes this way. Okay, well, if the coil itself is going to produce a field that goes down this way, if my fingers went through the coil, then using the curl rule, the current would rotate this direction, and that's why I actually have this drawn in so that the current flows this way. But if I remove that particular magnet, if I pull it out, now I'm reducing the flux or reducing the field lines, so the wire will actually work to create field lines up, and now it curls the other direction around this way. Okay, and again, this is probably going to be something where we're going to have to, try to demo it or have you use something to actually see what exactly is happening. You might have to actually have hands-on with some materials so that you can see that. Okay. All right. So that's Lenz's law. A current produced by an induced EMF moves in a direction so that its magnetic field opposes the original change in flux. So why exactly does that happen? Well, there's really just two fields. You have the changing magnetic field that actually causes the current, and then the magnetic field that is created by the current fights against it. Okay. Another piece that will affect this, obviously the distance between the coil and the magnet. As the magnet gets closer, the flux will increase, and that's kind of what I went through back here with this particular picture. Okay, if I was actually physically moving, the magnet towards this, the closer it got, the more lines would go through it. The closer the paper gets to the magnet, okay, the more lines flow through it. Now, I've got a little summary here. It says EMF is induced when there is a change in flux. So how exactly do you change the flux? Well, okay, we could increase the magnetic field. Okay, use a bigger magnet, something along those lines. We could change the area. So like here, if we had a thing of wire and we kept it in a nice circle, if I went ahead and I stretched the circle, made it more of an ellipse, okay, then that would actually have less area for it to go through. Okay. The other thing is you could change the orientation. You could change the angle to the field. As long as it is perpendicular to the field, then that would maximize the number of flux, or maximize the flux that could go through it. If I turned it so that it was parallel, then we wouldn't get anything out of it. Okay, so these are some of the factors that will affect magnetic flux.